We are back and we're actually getting to lecture material today. So hopefully you've watched that video with the introduction in terms of what's going to be covered in Engineering 110, what to expect moving forward. And so now we're going to actually get into some of the lecture material. So one of the basic things that we're going to be doing in instrumentation experimentation is essentially measuring physical quantities. So we're going to be making lots of measurements, and we are going to be designing. We're going to make measurements, and we're going to design experimental apparatuses in order to make measurements. So why are we even going through the process? This should be pretty straightforward, like what a measurement is, but it's becoming more and more difficult, or not more and more difficult, but we're trying to measure essentially quantities that are becoming much more difficult to measure than kind of previous experiments. So we are getting into extremely, we're looking for high resolution measurements in order to kind of solve essentially these new problems, these kind of new quantities. You could just think about a computer chip with Moore's law. Chips are getting smaller and smaller. We're getting into kind of the nanometer and even angstrom range in terms of the circuits that we can draw on a computer chip. So we need high resolution in order to kind of measure these properties in order to kind of break through the next bound of whatever material, whatever application you're looking at. So that's kind of the high level aspect of it. So keep that in mind as we go through now, kind of a little bit laborious derivations, or definitions. So, measurements. What is a measurement? Well, a measurement simply is a quantitative comparison between a predefined standard, so a standard and some measurand. So, there's lots of different types of measurements that we can make. A measurand is effectively just what are you measuring? So, what do you want to measure? So, what are some types of different measurements that we can make? Well, we can measure temperature, we can measure length, time, stress, strain, viscosity, force, torque. This list can go on and on and on and on and on. So I'm a material scientist, so I like to kind of put my material basically in some type of Insteron machine right here. So here's one grip, here's another grip. I am not an artist. You put your material, whether it be a cylindrical sample right here, and then you pull up on these jaws, uniaxial tension test, and you could develop a stress strain curve that you've definitely seen if you've taken my Engineering 45 course. So that's one type of measurement you can make. Again, it could be as simple as something as temperature, but again, temperature measurements, even just measuring, your weight, scale. So you step on a scale and you measure your mass in kilograms or grams, or kilograms or pounds. That is a simple definition of a measurement. So it meets the standard. It's a quantitative comparison, again, between some predefined standard and some measurand. So that's basically it. So measurand, just again, is basically your input quantity. So what are you measuring? Here, what do you want to measure? What do we measure? Now, standard has some relationship to what our measurand is. So it's related to our measurand. Typically, it's going to be of similar units, and then we'll kind of talk about standards on the next page right here. So what are some examples of standards? It's the kind of quantitative comparison. So a tape measure can be a standard. A balance, or like we said before, a scale, when you're kind of measuring your weight. Hopefully, if you're like me, I'm always trying to lose a little bit more weight, so hopefully that scale is a little bit off on the lighter side, but mine never seems to be that way. It's interesting. Anyways, speed of light, stopwatch, an extensometer. These are all kind of different standards that you use, again, to measure. You compare your measurand to some type of standard here. So that's kind of what we're dealing with. Now, there's different types of standards. There's primary standards. So primary, here. And then there's secondary standards. So primary standards really defines like what is, so for example, we define, we're looking for the primary standard for length. So in this course, we always use SI units. We will not, if you see any measurement that's not SI, you always convert. So we're going to be looking at meters, kilograms, seconds, newtons, joule, et cetera. So we will always be working in SI units. I will not, in this class, we will never work in non-SI units. So primary standard for length, we know we're going to be measuring in meters. That is going to be our unit. That is not our standard. The primary standard for length, we measure the meter relative to a very famous equation. Hopefully you've seen this. Many of you might not have worked with it before, but you've definitely seen it on a t-shirt, hopefully. So what is c here in this very somewhat famous equation? C is the speed of light. So we actually measure length. We can measure length extremely accurately with high precision, high resolution, using relative to the speed of light, essentially. So the energy equals mc squared. So we actually define what length is, a meter, via this standard, which is the speed of light. What about mass? Kilograms. Kilograms has actually a really funny story. Actually, before we get on that, so a secondary standard is anything that's calibrated based on this primary standard. So again, this could be a micrometer, which has an uncertainty of 1 micrometer. This could be a ruler, tape measure, etc., etc., etc. So lots of secondary standards, but there's only one primary standard. What about weight? I was going to tell my fun story. Well, kilogram actually has a really interesting. The primary standard for kilogram up until fall of 2018, the first time I taught this course, the primary standard was the international prototype. What it was, international prototype P, it was basically this little kind of cylinder, platinum iridium, that we defined as a kilogram. So it was just this one prototype, this one sample, and everything else, all the secondary standards in the world, a balance, scales, everything else that measured essentially weight or mass was calibrated based on this one sample. What's the problem with that? Well, the sample is, if we destroy that sample, we're in really big trouble, right? The other thing was, interestingly, year by year, they would measure this, and you'd get fluctuations in the measurement of about, I think it was like 50 micrograms. Now you're saying, Professor Simon, what's 50 micrograms? Relative, how is that really going to affect our, our lives? Well, let me give you an example. Titanium is about, from my time in industry, it hit about 140, and it's probably higher now, $140 per pound. And then we know that convert pound to kilogram. But anyways, so it's $140 per pound. We would generally, when I worked in industry in Pittsburgh, we would generally produce in one run somewhere between like 2,000 tons of titanium. If we're off plus or minus by 50 micrograms here, and that propagates through here, you're talking about a lot of money that you could possibly be off by. So what actually happened, and just recently, actually it was right at the end of the first time I was teaching this course, they redefined the primary standard to be Planck's constant. So hopefully you've seen this Planck's-Einstein relationship, that energy, basically a photon equals Planck's constant h. That's Planck's constant h, not h bar, times frequency. So they redefined it again based on kind of this fundamental equation. So you'll see that happen a lot. Temperature does the same thing. If you're looking at amperes, volts, et cetera, et cetera, et cetera. So those are just some ideas and examples of standards that you might run across. So why do we do, again, as engineers, we kind of know this answer, but what's the significance? Why do we make measurements? Why do we care so much about these ideas of precision and resolution? Why do we have to be so accurate? Well, it's critical that we understand essentially the system that we're working with and how that fits into those measurements that will determine essentially how our application works. So we need to measure systems, we need to experimentally measure parameters, because we need this quantitative information on the state of our system. And if any of you are you're interested in the study of thermodynamics, if you've taken a thermodynamic course, you know that in order to find thermodynamic equilibrium, we need to find all of these state variables. We need to understand what are the quantitative values here, and then we can see how our system will eventually evolve, or evolve will be in kinetics, but we will eventually then predict what will be the thermodynamic equilibrium state of our system. If you're more application and practically focused and you're not interested in kind of the thermodynamic theory behind this, measurements are critical for control processes. So temperature control on a sheet annealing line. So in industry, we would kind of basically have these huge rollers. You'd pass a sheet of metal through, and then you'd anneal basically in this kind of oven. So having really precise control in this oven is critical, because if you deviate for certain pieces of metal, if you deviate plus or minus 10 degrees C and even less, really plus or minus 5, you could produce an entirely different microstructure, and that's going to change the properties of your materials drastically. Yeah, so control processes, daily operations, again, AC, it's really hot right now here in Stockton, especially with the fires. So I'm cooking, so I need better temperature control at lower amperes, by the way. Anyways, establishing cost. So just like I just gave this example, oh, I remembered it. I'm still pretty good. It's important to kind of have these precise measurements to establish cost of materials and for applications. Temperature and bioreactors. I know there's a lot of bioengineers in this course. You could tell me better how that affects cell growth, but again, you could cause thermal necrosis in cells if temperatures aren't well. You can differentiate different cell types depending on the temperature and the environment. So it's critical that we know these. And then there's just so many other parameters, thermoconductivity, acceleration, all these different things that we could measure. The world is our oyster, but we need to have instrumentation so that we know we could measure these quantities. Now, in this course, one of the primary focuses and one of the problems I typically see not only with undergraduate reports or kind of publications, but even master students, even PhD students sometimes, is that a measurement is useless. You can never report to me if I tell you to measure, if I gave you a tensile specimen and I asked you to measure the length and you measured it and you do not give me an error bar, your measurement is useless. We need to know what is the uncertainty because no one can measure that value and get the same value every single time and then give it to another person and measure that exact same thing. So we need to understand when we make a measurement, what is our uncertainty, what is our error bars. In this course, in every presentation, every report that you present, every measurement should have an error bar. Otherwise, I will be a little bit upset. But again, it's because we need to know, we can't measure something with 100% certainty. So I want to see when you design your experiment, when you design your apparatus, what's the resolution? What is your error bar? What are your bounds? So I don't mean to kind of be too mean, but please put error bars on everything. It's a sticking point for me. So, and it's important too, because if you have error bars, if you're designing a material, if you're designing an application, and you just put, okay, it's this value, for example, that the UTS, the ultimate tensile strength of titanium is 100 megapascals. It's not. And you give me that value, and I design my application because I think it's exactly that value, but you failed to mention that at least when you measured it, it's 100 megapascals plus or minus 50. That's a big deal. You could cause critical failure, catastrophic failure. We don't want that to happen. So let's be a little bit careful. Again, engineering it's a wonderful field. It's an amazing field to work in, but there are real life consequences to the actions that you'll take when you get out of and into the real world. So there's one thing I want you to take with is error bars, uncertainty, put them everywhere. So now that I've scared you enough, we could talk about, there's basically two different categories of measurements that we're going to deal with. These being direct measurements and indirect measurements. Obviously, there's more, you could subcategorize everything, but every measurement can kind of fall into one of these two categories. One is easy and uncommon, this guy, hint, hint, and one is a little bit more difficult, but is more useful, especially as we measure, quantities that are much more difficult to work with. So let's talk about direct measurements first. So a direct measurement is kind of one of the easier measurements that you can make. So for example, if I have I gave that example of the dog bone here, dog bone sample. So if I wanted to measure just the length of this dog bone sample, and I basically took a ruler. So if I have a ruler and I want to measure the length, this would be an example of a direct measurement. So it just basically use a primary or secondary standard. Typically, you really don't use primary standards. You usually use a secondary standard, but again, it is possible in principle. So a secondary standard will typically be the one that you utilize. So a direct measurement, you take some measurand. So in our example, we wanted to measure length, the length of our dog bone specimen. We compare it against a secondary standard, that being a ruler. We did this process of comparison, which is the heart of our measurement, and we got a result, a readout. So we read on our ruler, so read on the ruler that it was, some value, X length. Exactly. So nice, right? I really wish life was this simple and straightforward. These direct measurements are nice measurements to make. We make them all the time in our daily lives, And often, they're a completely valid way of, making an experimental measurement. The problem is if we're, so for example, if I want to examine, okay, this tensile specimen, and I needed to make a really, really precise, I'm measuring, for example, I put a microcrack here. So a microcrack, oops. Because if you're taking my material science course, I wanted to see how a microcrack can influence the mechanical properties of this tensile specimen. And if I needed to measure the length of that microcrack, so that microcrack could typically be on the order of anywhere between nanometer, so sorry, 1 nanometer, so 1 times 10 to the minus 10, or 1 times 10 to the minus 9 meters, or even 1 angstrom, so 1 times 10 to the minus 10 meters. If you develop a ruler that you could just look at visually and measure these values, talk to me, because we need to make a startup and make a lot of money. But my point here is when you're trying to make measurements with this resolution, you cannot really use a direct measurement. We're going to need we need more accuracy, we need more precision, we need more resolution. So in practice, when you're looking at literature papers and scientific articles, you're not going to see many papers, if any, that use direct measurements. So it's a little bit less common. We need more precision. We need more resolution. I've been saying these words, precision, resolution, accuracy. It is going to be critical, and I'm going to, again, be very, using the correct terminology is extremely, extremely important when you're talking about making measurements. So I'm going to be really kind of strict in terms of when I read your lab reports, making sure that you're using the correct terminology when referring to these properties when you write your lab reports. So let's look at accuracy. So accuracy, precision, resolution, sensitivity. These all mean very, very distinct things. They are not the same. So accuracy is the difference between your measured value and the true value. So if I have, again, I'll just kind of draw it more simply. If I have a tensile specimen that the manufacturer says it should be 1 meter, and I measure it and it's 0.9 meters, my accuracy is this difference between the measured value and the true value. Precision is the difference between reported values during repeated measurements of the same quantity. What that means is if I take this sample now, and if I have my micrometer, and if I make 1,000 measurements, what is the of this length? What's going to be the difference? Or you could even talk about, we'll get into it a little bit, what's the standard deviation of those 1,000 measurements? If it's really, really small, if hopefully you've seen a distribution like this before. If my distribution is tight, my histogram is a function of length. If my distribution is tight, I have high precision. If it is wide, then I have extremely low precision. And resolution is the smallest increment of change in the measured value that can be determined by the readout scale. Resolution basically says how much can you measure. So I do some research where I put these kind of like biological samples on material here. So I put these little biological ligands, I roll magnetic particles on them, and I roll across the surface. I have resolution. I can detect particles at essentially picomolar, so 10 to the minus 12 molar concentrations, and even lower. Does that mean much to you? Really? No, but it's how much, how small of a value that you can measure. So going back to the example of the microcracks, if you can measure a nanometer or an angstrom, if you can measure an angstrom, you have higher resolution than the device where you can only measure a nanometer. So keep that in mind. And sensitivity is basically the output per unit change in the measured quantity. If you have higher sensitivity, it indicates finer resolution, better precision, higher accuracy. So just want to make sure, use that language properly and move forward. I'll be very, very interested, and I will be nitpicky on your lab reports. But again, it's really important going forward. You want to use the correct terminology because people make decisions based on the papers that you're going to write. So again, the good for humanity. So, all right. So what happens when we want to measure, for example, if I want to measure the strain in this material? So I want to produce a stress strain curve. Can I use that? Can I do that with a ruler? No, it doesn't have, again, what term? It does not have the resolution in order to measure those values. So I can't like look at strain or measure strain via my eye. So I'm going to have to basically build or create an experimental apparatus or use a device that is going to transduce the signal. So it's going to take strain, which I can't measure, convert it into some type of analogous form. Usually, well, for strain gauges, it's going to be a change in electrical resistance. It's just we're going to transduce the signal to some other form, and then we're going to convert back and measure strain or measure our measurand. So this is the second category, more difficult, much more common, an indirect measurement. So again, we're going to use some type of transducing device. We're going to convert the input signal to some analogous form, and then we're going to measure. So during this kind of process where you transduce the signal, that whatever the analogous signal is, usually it's an electrical signal, but it could vary. We're going to see lots of different examples coming up soon. The analogous signal can be processed. So I could process my analogous signal using amplification, filtration, integration, or any other mathematical operation in order to, again, improve the resolution of my apparatus, and then also that will lead to changes in my precision as well. So indirect measurements, there's basically 3 stages in terms of how that measurement takes place. So the first stage is the sensor transducer stage. So we have some type of measurand, and we convert it into some analogous signal. And when you're basically developing that sensor transducer device, it should be insensitive to the input. So basically, we don't want if that sensor transducer varies with temperature and you're in a hot environment, it can throw off your measurement, cause drift. We don't want that to happen at all. The second stage is kind of what I previously mentioned as well, is this signal conditioning stage. So we are going to, once we convert that signal into some type of analogous signal that we want to work with, we can do some operations to kind of clean up that signal. So we can amplify that signal, we could filter that signal, we could do basically any mathematical operation in order to kind of improve the signal or to kind of get back. Usually this mathematical operation is used to get back to the measurand, our measurand, or what we're trying to measure initially. So that's kind of the purpose of that second stage there. Now, the signals can vary. Usually, every measurand is going to vary in time. So once you kind of transduce that signal, you could be dealing with analog signals, you could be dealing with digital signals, and they are going to be very different in terms of how you're going to work with them. Additionally, these signals that vary on time can, basically there's different time dependencies. So it could be static or constant in time. So if you run kind of like a creep test where you hold, some quantity constant, these are not going to be too often, or a static measurement could be, a scale. So that's not going to kind of vary in time. Dynamic, there's lots of kind of dynamic measurements, right? So you could do fatigue testing where you change essentially the stress amplitude as a function of time. There's lots of dynamic signals. And then those dynamic signals that vary in time can be periodic. They could be completely non-repetitive or transient. They could be single pulse. So like when you do a fracture impact test. They could be random. We're going to deal a lot with this. Again, this is where our Fourier analysis comes into play. Fun coming up in exam 2. And then finally, we have our readout or recording stage. So once everything has been done, the signal has been processed, we've converted back, then we just get a readout. So typically this is done as a computer readout, or you get some type of table or data file, and then you still might have to do some post-processing. Ideally, you want to develop your apparatus that it does all of the operations and all of there's no post-process, but realistically, as an experimentalist and as a researcher, that's never the case, because we're measuring something and then we're going to try to figure out and do the analysis later. So we want to just grab that raw data and we'll do the data analysis later. And in this class, we're going to be doing that data analysis with, you guessed it, mathematics. So more on that later. So yeah, we're going to do some examples. Again, this is a lot of theory. I think this will become much more clear once we actually do some real examples. That will be on the next video. So that'll be much more fun. We'll do some examples that you'll see that you'll actually have to deal with in lab. And that's that. All right. Hope you have a great day. And yeah, let me know if you have any questions. Thanks. Bye.